Okay, this is an opportunity for you to listen to my lecture. Of course, one of the nice things about doing it this way is you can pause and think. You can repeat a slide or a portion of the presentation if you want to do that, or you could listen to the entire thing all over again multiple times if you're really feeling like it. But I'm going to talk today about a couple of different concepts. And when I finish with a concept, it might not be a bad idea to pause and work on the worksheet. And when you come to a portion of the worksheet that maybe you don't understand, you can come back to the presentation and then, sort of go that way through your assignment for today. Okay, but we're going to start today with the concept of the mole. What is a mole? Now, the mole is a count. It's a large count of things. So if you know what a dozen is, I'm sure you know what a dozen is, you know that that's a count of 12, right? So if I say a dozen eggs, I mean 12 eggs. And naturally, if I say 3 dozen eggs, you know that means 3 times 12, 36 eggs, right? We do the exact same thing with the mole, except that the number is much, much bigger. Okay, the number is actually 602 sextillion. Sextillion is 21 zeros. Okay, so 602 sextillion comes out to be 6.02 times 10 to the 23rd things. Okay, a mole is some count of things. It's usually used for atoms or molecules or ions, or in the case of ionic compounds, we talk about formula units. Okay, but it's that big number of those things. Okay. You need to know this number, so go ahead and commit it to memory. All right, that would be a really good idea because we will refer to it quite a bit. Now, the nice thing about the mole, one of the really nice things about the mole, and it's not a coincidence, but the mass of a mole of something in grams is equal to a mass of a single item of the thing in AMU. For example, 1 molecule of water has a mass of 18 AMU, atomic mass units, right? 1 mole of water molecules has a mass of 18 grams. So notice the numbers stay the same, the unit just changes, right? So if I multiply an AMU times Avogadro's number, I end up with a gram, is essentially what that means. Now, it's kind of interesting to think about how much is actually in a mole, right? So if 18 grams of water is a mole of water, how much is 18 grams? Well, that's 18 milliliters. That's not actually all that much, right? If you think about your smallest beaker I usually give you as a 50 mil beaker, it's less than half of that, right? So that little bitty beaker, less than half of that contains an entire mole. A lot of you walk around with hydro flasks, right? Those hydro flasks, I think a lot of them are 32 ounces. They would have more than 50 moles of water molecules in them. So that just gives you something of an idea of it's not all that much stuff, and yet it's a huge number of molecules. And of course, this is because the molecule is such a small thing. Now, note that because the mass of something is, is given here in grams per mole, really, right? It's grams per mole of water, 18 grams per mole of water. That is actually going to be used as a conversion factor. So if we say that 1 mole of water is equal to 18 grams of water, we can now use 18 grams per mole as a conversion factor, and we will. All right, so 1 mole of carbon is 12.011 grams of carbon, right? That's also going to be a conversion factor. So 12.011 grams per mole. Is the conversion factor you would use in order to go between grams of carbon and moles of carbon. All right, so this leads us to what we call the molar mass. Okay, this is the mass per mole of a substance. As I said, you can talk about 12.011 grams per mole of carbon. You can also get the molar mass of a compound. Okay, you can get it for an atom, for an element. You can get it for a compound. So the procedure for doing so is very simple, very straightforward. You figure out how many atoms of each different element there are in your formula. Okay, then you look up the molar mass in your periodic table for each one of the elements. Then you multiply the number of atoms times the molar mass for each of the elements, and then you add these products together. Okay, and I'll take you through an example so you can see this in action. All right, but it's pretty simple. All right, so here's how we do it. We'll take the example of ethane, right? C2H6. Of course, in C2H6, there are 2 carbons and there are 6 hydrogens. So I count those up. That's the first step. Second step is I look up the molar mass in my periodic table for carbon and hydrogen. Carbon is 12.011 grams per mole, we said, and hydrogen is 1.008 grams per mole. And then we multiply the number of carbons by the molar mass of carbon. And so 2 times 12.011, right? And we do the same thing with hydrogen. So it's 6 times 1.008. And now we have the products, you see there, 24 and change and 6 and change, right? And then you add those up in the last step, and you end up with 30.070 grams per mole. So ethane, 30.070 grams of ethane is equal to 1 mole of ethane, right? And again, we can use this now as a conversion factor, and we will. One note that I ought to bring into this is that the notion of a formula unit, you'll hear this term thrown around occasionally. So you know how we have molecules for molecular compounds? Well, we don't have molecules for ionic compounds, right? Instead, we said that they come in these big crystals, like the picture on the right, where you have repeating patterns of sodium and chloride, and sodium and chloride, and sodium and chloride, and so on, right? So instead of talking about a molecule of that, we talk about just one unit of that ionic compound being what we call a formula unit, or often I will abbreviate that to just FU. Now, don't take it personally, right? But, you know, this is just a quick way to write formula unit. So we can also talk about the molar mass of the formula unit, okay? And this is what we do with ionic compounds. We obviously don't have a molar mass of the molecule. We have a molar mass of the formula unit. So in the case of NaCl, it would be 58.443 grams per mole because you just have one Na and one Cl in that formula unit. Now, I keep talking about the fact that these are going to be used as conversion factors, right? And what I mean by that is you will be able to convert between the mass of a compound and the moles of that compound, the mass in grams, of course, and the moles of that compound. In order to do so, you convert back and forth with the molar mass. Now, if you're going to go from grams to moles, you're going to divide by the molar mass. If you're going to go from moles to grams to mass, then you have to multiply by the molar mass. All right? And again, the molar mass depends on what compound you're talking about. So this is a variable thing. You also have conversion factors. We also have another conversion factor. Avogadro's number itself is a conversion factor, and it converts between moles and the number of things. By things, I mean ions or molecules or atoms or whatever, you know, thing you're talking about. Okay? So we've got both of these different conversion factors. Now I want you to note something. In both cases, when you go from moles to something else, you're always going to get a bigger number. Okay? Moles are a manageable. One of the reasons we like moles is they are a very manageable number, right? All of the atoms in my hand that I put, you know, that I can put in my hand might only add up to 1 or 2 moles. So that's a very manageable amount, right? But the mass may be a very much bigger number. And so when you go from moles to grams, you're going to get a bigger number. You're going to get, so you're going to multiply by the molar mass. In a much bigger way, when you go from moles to the number of things, the actual number of molecules or atoms, it's going to get way bigger, right? So really that, you know, that arrow should be going way further away, but, you know, for the sake of simplicity, I just made it just the same size. But you're going to be multiplying by Avogadro's number whenever you go from moles to the number of things. When you convert back 2 moles from either of those, of course, you're going to divide. Okay, so you get back a smaller number again. All right, I'm going to show you a couple of examples of this. So for instance, if I was to give you a 5-gram sample of aluminum and ask you how many moles of aluminum atoms there are, this is the procedure you would take. Now, please excuse my ugly penmanship. This was me attempting to use my trackpad to write the problem, and it sort of works. But you have 5.0 grams of aluminum, right? That is your given. Now I've set this up with a T-chart, just like we did with conversions, right? And so I know I'm converting into moles because that's the question, right? The question is how many moles are there? And so I've got to put moles in the numerator, right? I've got to put it in the top. And then I've got to divide by the number of grams, right? That way I cancel grams on both sides. So I've set up my conversion factor appropriately. Notice that in order to go from grams to moles, I am dividing by the molar mass. That's effectively what I'm doing. But when I set it up with the T-chart, it's very easy to see that grams cancel with grams, leaving me with moles, which is my answer. Okay, and so then you do the division, and you get 0.19 moles of aluminum. All right, now here's a slightly more complex version of this problem. It says, how many molecules of water are there in 52.0 grams of water? Okay, now notice that it's asking you for molecules and giving you grams. If you go back to my little schematic diagram here, you'll see that if I start with grams and I'm looking for the number of things, then I've got to convert through moles. So I'm going to actually have to convert to moles and then from moles into things. And so you can see that's what I did, right? I divide by the molar mass of water, which I can find to be 18.015 grams per mole. And that will give me, if I cancel out the grams, it'll give me moles of water. And then I will multiply by Avogadro's number to get into molecules. And so you see the multiplication by Avogadro's number per mole, right? Molecules per mole. And again, this cancels out moles, right? Leaving me with molecules of water, which is what the question asked for. And you can see my answer. It's a very big number, which makes sense, right? There's a lot of molecules of water in a small glass of water. This is effectively a very small glass of water. All right, so you can see how many. That's actually septillion, right? 1.74 septillion molecules. It's a lot of zeros. Okay, this would be a good time to pause the video and to go ahead